So good afternoon, everyone. So hope you had a great lunch. So I'm Lingzhi Wang, and I'm very happy and honored to be here to present our newest work incorporating gradients to rules towards lightweight, adaptive, provenance-based intrusion detection. So let's just start from some introducing about intrusion detection and provenance graph. So the advanced cyber attacks, such as APT attacks, brings new challenges to the traditional intrusion detection system because they are more advanced. Usually, the attacker use sophisticated techniques such as zero-day exploits, customized malware, and they are more persistent. Usually, the attackers may remain undetected for several days to several months, and they are more targeted. So these properties make it even harder for the traditional intrusion detection system to detect such cyber attacks. So in recent years, people find it's very useful to use a provenance graph to record the system activities, where the nodes in the graph represent the system entities such as processes, files, and network sockets. And the edges in the graph represents the interactions between these entities. For example, the process may read a file or send some data to the network socket. So this graph actually provides us a more comprehensive context. It allows us to correlate different system entities, and it gives us a wider scope against the APT attacks. So the existing provenance-based intrusion detection system can be roughly divided into two categories. The first one is a rule-based PIDS, where we use a simple static rules to model the graph patterns. And another category, which is the embedding-based PIDS, is very active in recent years. In this category, people use embedding functions to learn the graph features from the provenance graph, and they use some tools like graph neural network to extract the feature vectors from the provenance graph and use these vectors for the following detection. So what's the problem? The problem is people love rule-based PIDS because it's very fast, it's very efficient, it's very lightweight, and the detection process is fully explicable. But it usually suffers low accuracy because the rigid and inflexible rules, it cannot be adapted to new detection environments or new data patterns. And some people may say, okay, let's just use embedding-based PIDS because it has a more powerful feature extraction function, and it has a learning capability, and it can adapt to new data patterns. But the downside of embedding-based PIDS is very expensive to perform such detection. For example, as we all know, usually any calculation using the neural network is very, very expensive, and we need to suffer the long detection latency and inexplicable detection process. So here comes our motivation. So we want to ask the question, is it possible to maintain the lightweight and the efficiency of the rule-based detection system while enabling the dynamic and automatic rule learning? So here's what we want to do. We have a set of detection rules, and we want to use this set of rules to perform the detection, and of course, we can get the detection results. And our question is, how do we adjust the detection rules to improve the detection results? So to answer this question, we need to model how the rules affect the final detection result. And our answer is gradients. Yes, we got our inspiration from the parameter learning process of the gradient-based method, as we may be very familiar with, like the training of the neural network. We initialize some parameters, and we use this set of parameters to perform some machine learning tasks, and we calculate the loss and also the gradients to the loss. And we use these gradients to update the parameters again and again until we find the optimal parameters. What we want to do is very similar to this process. We want to first initialize our rules, and we want to perform the detection using this set of rules. And we calculate the loss as well as the gradients, and we apply those gradients to update the rules. So here comes our one sentence takeaway. In this work, we just transform the non-differentiable rule-based detection process to a differentiable function so that we can use the gradient-based optimizing algorithm to fine-tune the detection rules. So basically, we just turn the detection process to a differentiable function. So let's dive deeper into the details. In this paper, we use attack propagation, which is one of the major mechanisms of rule-based detection. It's kind of similar to the taint analysis. So in this part of the attack propagation, we assign some tags to the nodes on the provenance graph, probably some malicious tags as shown in the red nodes. And as the event occurring, we propagate the malicious tag among the entire provenance graph. And by applying the alarm triggering rules, we can get some alarms in this detection process. And here are some challenges in the tag propagation process of the intrusion detection system. The first one is how to initialize the tags of nodes. So how to assign the initial untrusted nodes to this entire provenance graph. So the tricky part is if we assign too many untrusted tags, we will face excessively amount of false alarms. So if we have too many trusted tags, we may have the risk of missing some attacks. So the second second challenge is how to propagate the tags among those nodes. So as you can see in this example, all nodes in the provenance graph had the red untrusted tag, which is usually unacceptable in the real-world detection because we will have excessively amount of false alarms. And the third challenge is how do we fine-tune the alarm generation rules? So when should we trigger an alarm, and how to control the sensitivities for specific events or specific alarms? And in addition to these challenges, previously all the rules should be set and adjusted by the human experts, which we want to do it automatically in this paper. So let's incorporate gradients. We propose Captain to address the dilemma between the detection accuracy and detection efficiency, where we incorporate gradient descent idea to optimizing the traditional rule-based detection systems. And due to the time limit, I may not have enough time to cover all the details of our system, but I do want to answer some key questions. The first one is how do we convert the rules to parameters? Because with the gradients, we can learn the numerical parameters, but how do we transfer the rules to the parameters? So in this paper, we designed three different set of rules, three different set of adaptive parameters to convert the traditional rules to the numerical parameters. The first one is the tag initialization rules, where we use the integrity score to show how we initialize the tag of each node. And for tag propagation rules, we use a propagation rate, which is a number, to replace the traditional tag propagation rules. And we use alarm threshold to replace the traditional alarm triggering rules. So with these three types of adaptive parameters, we can assign different rules for each different node and edge on the provenance graph. And we have the finer granularity to control our entire provenance-based intrusion detection system. So second key question, how to calculate the gradients? So we just record and update the gradients during the tag propagation. So we initialize the initial value according to the default settings, and we just perform tag propagation. And every time if the tag is changed, we just update and record the corresponding gradients. As you can see, the numerical tags are propagated among this entire provenance graph, and we update the gradient table accordingly. So this gradient table basically just records the influence of the rule parameters to the final detection result. So with these gradients, how to update or train the rule parameters. So say we have the misdetection on the training sets, we just calculate the loss when there is, for example, when there is a false alarm on the training sets, and we just look up the gradient table to see which rule parameters is related to this misdetection. And we just apply the gradients to update the new value of the corresponding parameters. And we repeated this process again and again until the convergence, and we apply the learned parameters in the real testing. So let's take a look at the evaluation results. So we evaluate our system on the public DARPA dataset and our own private datasets. Compared with the recent work, our system can greatly reduce the false alarm by a huge margin and maintain the similar true positive rate to the baselines. Basically, it just says we can detect all the attacks on our datasets. And a more impressive result on efficiency, here's the results. So compared with existing embedding-based PIDS, our system can reduce the detection latency, the CPU usage, and the memory usage by a huge amount. And even compared with the existing rule-based PIDS, we only add a slightly additional overhead. And as we mentioned before, we achieved a significantly reduction in terms of the false alarm and significant improvement on the accuracy. So we also present some case studies in our paper. So as a rule-based detection system, each alarm from our system has a clear semantics and explicable detection process. And because we assign different parameters to each different node and edges on the graph, so our system can distinguish between very, very similar graph patterns, and we can also address the tag or dependency explosion issue, which is faced by many provenance-based intrusion detection systems. And here comes our conclusion. So in this paper, we address the dilemma between detection accuracy and efficiency faced by the rule-based PIDS and embedding-based PIDS by incorporating the gradient-based optimizing algorithm to the traditional rule-based detection. And in the future, we are trying to incorporating the human knowledge into improve the intrusion detection system, and all our code and experiments can be publicly accessible in our GitHub repo. And thanks for your listening, and I'm happy to take your questions.
Thank the speaker.
Thanks.
Thank you. Any questions? There are microphones, 2 microphones across the room. We have time for a question or two. Please state your name and affiliation. Go for it.
Hi, my name is Adrian from Purdue University. Thank you for the talk. I guess my question is, have you tested how efficient is your proposed framework? Because you mentioned that you need to do the parameters update for every 4 alarms. Have you actually tested any overhead, or do you have an estimation of how efficient it is if you actually deploy this to a real system?
So it's very efficient in the testing phase, but it will add some overhead in the training stage because we need to record all the gradients. But because the training process can be done offline, so probably we can just train the entire detection system, use the offline data, and we just apply our system for detection. And for the testing or detection phase, it's very efficient because we don't need to record any more gradients. We just apply it as a traditional rule-based detection system. So it should be very efficient and fast.
All right, thank you.
Yep.
Okay, that's all the time we have for questions. So let's thank our speaker again.
Yep. Thanks.